going to use de Moivre's theorem now to solve this equation. The reason I know that we're going to use de Moivre's theorem is because there's a power here. So as soon as you see that, you think about de Moivre. So de Moivre's theorem, it's very hard to spell. All right, so the first thing we need to do here is we need to make an assumption on the form that z is going to be as a solution. So we let z equal r cis theta. The key thing with de Moivre's theorem, remember, is that everything has to be in cis form. So we're also going to transform 1 plus I into cis form. So we're going to convert 1 plus I into cis form. So remember that to do that, you can do a sketch, and a quick sketch will show you that a 1 and plus I, which is here, gives us a complex number that is 45 degrees this way, so pi on 4, so our arg theta is pi on 4, and for our value, which we'd say, which we'd call r, normally, you know, because we've already used theta for z, I should, strictly speaking, use a different symbol here. We'll use phi. Phi is the angle with the circle with a line through it, and we'll just call this r1 for our other magnitude. You could also call that straight up just the magnitude of 1 plus I, and that's the square root of 1 squared. Remember the real part plus the imaginary part squared, which is 1. Don't include the I, it's just the coefficient. So this is going to be square root of 2. So that means that 1 plus I in cis form is root 2 cis pi on 4. Okay, so now what we can find is if we're saying that z squared equals 1 plus I, that means that z, remember that this is z, and I'm going to put a box around that so we can remember, z is r cis theta. I'm going to put that into the place of z, square it, equals 1 plus I. 1 plus I is now in cis form as well. So that's going to be root 2 cis pi on 4. Okay. Now I'm going to use de Moivre's theorem. Remember that when you have powers, the power becomes a power on the r, but it multiplies the angle. So we're going to have here r squared cis 2 theta equals root 2 cis pi on 4. Let's put the pi there properly. So now what we can do is we can actually equate the different parts of this equation. Remember that the magnitudes out the front need to be equal to each other, and the angles need to also be equal to each other. The other thing to remember here is that pi on 4 is the angle here, but it could also be pi on 4 plus 2 pi, plus 4 pi, or even minus 2 pi. So we're going to take that into account too. So we have two equations here. The first one is that r squared equals the square root of 2. So that means that r has to be equal to, now it's going to be the square root again of the square root, if that makes sense. So I've already got the square root, and we're going to do that to the power of a half. Now this is where we're going to start using fractional powers now instead of using roots. So we have r equals, the square root of 2 is 2 to the power of a half, and we have the half outside the bracket. Now remember that if you have powers next to each other, they multiply. Oops. So this actually will turn into 2 to the power of 1/4, or the fourth root of 2. So that's what r is. So therefore, r equals 2 to the power of 1/4. And that is really important because we've actually half solved our equation now. We know what the r is here. Remember that we're trying to solve, and we're trying to solve for z. So if we've found what r is, we're halfway there. Now we've got these equalities here too on the angles. So we have also 2 theta equals this thing here, this angle, pi on 4, plus 2k pi. We say that because k can be anything, and actually I'm just going to write this in this form, because k gives us that cyclical nature of the angles. You can keep going round and round, or going back the other way, keep going round and round. So we're going to solve this now. So we have theta equals, divide both sides by 2. Okay, so I've got theta equals pi over 8, because dividing by 2, that would be pi over 8, plus k pi divided by 2. Okay, so divide both sides by 2. And now what we need to do is actually find our different angles. Now the key here is what is the power that you're looking at, how many roots will you then have? Okay, so we're going to have 2 roots because the power is squared. So let's check 2 different values here. Now remember that k can be anything, 0, plus or minus 1, plus or minus 2. Because we only need 2 solutions, we're just going to always start with 0, check k equals 0, and then you just keep going k equals 1, k equals 2, until you have the right number of roots that you need. So for k equals 0, I'm going to put that into here, and I'll straight up get theta, which is nice. K equals 0 is just 0. So this is pi over 8. And let's put in k equals 1. We're going to get pi over 8 plus 1 times pi. Pi is 8 over 8, so that's 9 pi over 8. Okay. So if we think about this now, this is a little bit over pi, 1/8 over pi. Now we only need those 2 angles because we have 2 roots. You don't need to write this down, but I'll just show you what happens if you go one step further. If I pick another k, if I put k equals 2 in, you're going to get theta equals pi over 8 plus 2 pi. And that would be, 2 pi is 16, that would be 17 pi over 8, which is exactly the same as pi over 8, because you've just gone around again to here. You've ended up back in the same spot. So these 2 are repeated. And this pattern will keep repeating. Pi over 8, 9 pi over 8, pi over 8, 9 pi over 8. It's just going to keep repeating. So there's no point in going any further than this. You could give this in arg form as well. Arg form, this would be negative 7 pi over 8, because you're 1 over here, pi over 8 here. Okay, so our 2 roots that we have are going to be Z1. I always label them, Z1 and Z2. Remember that Z equals R cis theta. We've found R, and we've also found 2 different values for theta. This one and this one. There are 2 thetas for our 2 roots. So our first root is going to be 2 to the power of 1/4 cis and the angle pi over 8. And the second root is going to be 2 to the power of 1/4. That was my R that I found. Cis negative 7 pi over 8. Now, that is all that's asked for here in this particular question. I just wanted to show you a little bit extra with that, which is what the graph will look like. So I'm just going to get rid of this part here. I'll just get rid of that part. So for the graph, I'm just going to use the calculator here. So 2 to the power of 1/4 is roughly, let's use the calculator, 2 to the power of 1/4, and we want to do that as an approximate, control and then enter. 1.18, okay, so it's going to have a distance of about 1.18. So I'm going to graph this. So we've got coordinate axes here. So this is the argon plane, imaginary Z, real Z. This is not necessary. This is actually the end of the problem here. Okay, this is just extra so you can see. What I'm going to do here is look at these angles here. Or these complex numbers, I'm just going to sketch them. So pi over 8, if we imagine that this is, pi over 8 is half of 45 degrees, it's about here. Okay, and let's say it's about there. And we'll call that Z1. Now Z2, the other root, is actually this way. So if we think about the angles here, this is pi over 8 here. If we continue that line down, this is pi over 8 here as well, then we know that our other complex root is going to be here. And both of those roots are the same distance away from the origin. They're both 2 to the power of 1/4, or approximately 1.18 away from the origin. And the neat thing about this is, because we have 2 roots from this equation, remember that when we talk about roots with de Moivre's theorem, they always have to be equally spaced. So check it out, they're both 180 degrees from each other. So effectively here, if you think about a simple way of writing this, Z1 is actually equal to negative Z2. Negative Z2 puts it the same distance from the origin, but just on the other side. So the nice thing with squared equations in particular is if you're finding roots, once you find one of the roots, you can actually just subtract or multiply that root by -1 to get the other root. They're always like that. If one is z, the other is -z. So that's the way that you use de Moivre's theorem to find the roots for a given equation.